Right, so we'll continue a bit, and now I've also included the simulator, and we had a discussion on a simple common source stage like this, where we have capacitive load and a driving NMOS transistor and an active load PMOS transistor acting like a current source. We had a bias voltage. Each of these guys also has a certain size, W over L, and this guy also has W over L. And we also have an input level and an output level. So questions then could be how to design the, this is frequency, the gain transfer characteristics, P1, A0 and omega UG. And what parameters do we have that actually define these transfer characteristics in the frequency domain? Well, quite a few. I mean, we have VB, the bias voltage. If I change the voltage here, I will influence the current of that transistor, which will change the operating point. Same with W, same with L. Same with input voltage, same with W over L for the NMOS transistor. And to some extent also the load capacitance. And something which is hidden here is the channel length modulation of these transistors that affect the P1, the output conductance or impedance of this device. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, VDD, 11 design parameters. So it's a very large set that we have to run through in order to understand more about how does this curve move back and forth with different settings here. Could I just increase the W and make this really, really large in order to increase the gain? Question mark. And we will not come to any solution today. I'm just going to demonstrate a little bit with the simulator. However, before we do that, this is our basis, and we can eliminate some of these parameters by adding a quite clever help circuit on the left here, and that we do with something we refer to as a current mirror. So I take a PMOS with the same size as this guy, like that, and I connect it like a diode. I connect gate with drain, and then I connect that to a current source like this, I. Let's call it IQ. And then by controlling this current, I will get IQ here. And the current mirror, since these are of equal size and they have the same gate voltage, that will force this current to be approximately at least equally large. And that means I can now eliminate VB more or less from the discussion. I can eliminate W and L more or less from the discussion. And I only have IQ, so I sort of reduce my parameter set a bit. I add 1, of course, but I also get rid of 3, so then I'm down at 8 parameters. Well, 9. Alright, and I can do other tricks like this. I could, for example, lock the channel length and also only use the minimum available, for example, etc, etc. So there are certain tricks we can do here. VDD typically given by sort of standard supply that you have available on your chip, and IQ times VDD, for example, could be a constraint from a, say, power consumption point of view. We know, for example, that P here is equal to VDD times the current through this branch times the current through that branch, so IQ plus IQ. So for example, if I have a requirement on P, maybe it should be less than a milliwatt or whatever, for example, then I can use that to reduce my parameter set even more than. So that's part of the course, to try to find ways to reduce this parameter set and understand what they're doing. We will find that some of the parameters we change do not help us in a beneficial way, or they have no impact. Well, why touch them then? Leave them as is. and then focus on the parameters that have great impact on the transfer function. Alright, so let's just take a very quick look on the circuitry here, like this. And maybe we can put this here. Alright, so this is my current source on the left hand side, like we had on the paper here. I have drawn it upside down with a negative current, in case you wonder. And then I have a PMOS. We're using multisim, by the way, from National Instruments. You have licenses available for that within the university. We have the transistor on this side connecting like a diode, and then with the same gate voltage to the other transistor, acting like a current source, where we can control the current with this current source, ideal current source, and then connecting to the drive transistor, which is connected to, which has its source connected to ground, which means it's connected to the common node, hence the name common source then. Alright, so yeah, so some ideas here could be to, for example, look at the gain transfer characteristics as a function of this current. So what I have done now is that I simulate an AC analysis. I assume we have a small sinusoid on this voltage source at the input, and then measure how much that sinusoid is amplified at the output. And that gives us a parameter set like this, because what I do is that I sweep my input current or bias current through the branch from 25 to 23 microamps, and then I can measure the gain. And then we see, for example, that the gain increases with higher current. We see that the omega UG increases slightly, frequency at the gain at high frequencies, and we will also see that the pole increases, it shifts towards higher frequencies. In this tool, you can also sweep, for example, we might want to alter the DC voltage on this guy. So you can go to the parameter set in this tool, and then we go to document. We want to do a AC sweep, but we want to vary the V in voltage and the DC operating point voltage. And we want to do a linear sweep, for example, from, let's do small increments, 0.375, sorry, 375 millivolts to 395 millivolts, and a step of 5 millivolts. And then I do my iteration here. And let's zoom out a bit. Let's set the axis to linear scale. Oh, let's do logarithmic. And maximum being 200 perhaps. Then we fit all of them. So 385 gives us a high gain. 380 less and less, etc. Bad, poor gain. So we see that the increase of gain happens when we increase the voltage to some extent, but then you have a couple of bullets giving you worse gain for higher input voltage. So this is some sort of sweet spot somewhere here. So 375 millivolts gives you worse gain, but also 390. So 385 seems to be some sort of optimum, which I have already tuned for. So let's look at the DC sweep like this, and let's look at the curve. So what I'm doing here is that I'm sweeping the DC voltage at the input gate, this guy, from 0 to 1.2 volts, 1.2 volts on the supply, I have 30 microns going through the branch, and then I alter the DC voltage here to find my operating point. So I was moving around here at 385, which I had selected to be roughly in the middle of the range. And then I did very small changes around that operating point from less to more. And we could see that we had some sort of sweet spot. And that's exactly what we see here. We have a very, very steep transition here, or tangent of the curve. So the slope of the curve is my AC gain. So going up this curve, reducing the input voltage, that also decreases the gain because the slope is less. And then going in this direction, I also decrease my gain because the slope goes worse here. And there are a couple of mechanisms. In the lecture we sketched this curve, and we could see, for example, that when we are below the threshold voltage, the transistor is turned off and the output is pulled high towards VDD up till the threshold voltage, 200 millivolts in this case. And if we look at the transistor, I've actually also set the threshold voltage to 200 millivolts, so that makes sense. So now we turn on the transistor, but the output voltage is really high, and these guys does not seem to have a good gain, even though it potentially should have. But that's because the fact that these transistors operate now in the linear region, so they act like a resistor rather than a current source, until a point when I have reduced the output voltage so much that these guys now come back into saturation region, and that's when I enter this phase here. So I have really high gain, and then at some point with too high input voltage, too low output voltage, then I push this transistor into the linear region, and then it also loses gain. So I should be somewhere here in the middle. And yeah, we could, for the fun of it, we could do a parameter sweep here of, say, let's see if we can make a parameter sweep of a transistor. Parameter like that, and then document, and let's see if we can do that component Q1, and we want to sweep parameter W down here, channel width, maybe from 100 to, let's make 220 microns with steps of 1 micron, and then the unit must be greater than, sorry, okay, that was too small, he thought, 2 microns then. Alright, and then we want to run a AC sweep. So here is another way of seeing that how the different parameters can affect the results. So I've already found the sweet spot more or less. So increasing the width in this case doesn't really help us, just reduces the gain. So it's really sensitive also. Okay, just some ideas to continue until lecture 2. So please have a look at the material and the ways how we can reduce the parameter set and understand more of how these different terms move around. How does this AC characteristics depend on the DC characteristics, where I have a very high slope like this, V in and V out like this. If I select different points here, what's the effect on the gain here, and how can we mitigate that? We will see eventually that the good answer to all these questions is feedback. If I could only spell it correctly, then it will be even better.